So, let us start with this steady 1D pipe network HC, which is Hardy cross discharge configuration 1. So, we will try to utilize the same structure as we have used in case of gradually varied flow, but fundamental difference is that we do not require that much computational effort like our gradually varied flow. Let us start with this CLC clear. This is this was there for GVF, but will not utilize it. This given data G is 9.81 global, EPS max, this is required for convergence 1 into 10 to the power minus 6, beta value beta it is 2, pipe number, pipe n is pipe number. So, we have 8 pipes, number of maximum number of pipes connected to a particular loop, we have 4. This is required for a loop connectivity matrix that I have discussed already. Now, junction number, this junction number is 5, and P loop is for pseudo loop and I loop is for interior loop. Now, loop number, which is the total number of loops, we have P loop plus I loop, that means number of pseudo loops plus number of interior or internal loops. Now, we have specified the discharge values directly without sign. Please check this thing, I have not used any sign here, and we have head difference 20 between two tanks or reservoirs. In this case, this is the loop connectivity matrix. Now, we need to construct one pipe connectivity matrix. So, what is that? That means in pipe 1, starting from pipe 1 to up to 8, we need to provide certain information. What is the information? Information is that in that matrix we will have a first column which is for first loop, second column is second loop, third column is for third loop. Why this is required? This is required during our delta QL update. So, this one, it is connected to first loop only. So, we will write it as 1, second one it is connected to second one and first one. So, I will write it as 1 and 2 both. So, like that we can enter the loop connectivity or connected pipe connectivity in a particular loop, and we can provide this information during calculation. Now, we have straightway this KV values, KV is nothing but KI cap. Now, again we need to specify this QV. What is QV? Zeros loop number, So, Lth loop and up to maximum number of pipes connected in a particular loop, we need to create this QV matrix, because this is the main matrix that is required for our calculation, because we need to preserve the sign convention in this matrix itself. Now, for general identification, we have this QV, we need to transfer our initial values. If loop connectivity L I plus 1, which is starting from second column of the loop connectivity matrix, if it is positive, then Q should be positive for that loop. Otherwise, what it means, let us see our loop connectivity matrix. If loop connectivity for first entry, this is negative, the sign gives us negative for negative value or minus 1 for negative value, plus 1 for positive value. So, sign multiplied by Qi value I have specified without any sign. So, I should input these values within this QVLI with this sign. So, sign should be coming from this loop connectivity matrix directly. Now, with this information or initial information, I can start this iteration. Obviously, in this case we have only space loop or this loop or for iteration, counter equals to 0, RMS equals to 1. So, that I can enter into this while loop, this RMS equals to 0, del QL zeros loop n 1, that means for each loop I have specified 1 del Q. Now, this part is important for our calculation. For L equals to 1 to loop number NR dr, numerator at denominator, if L less than equals to P loop, that means less than equals to number of P loops, then we need to add this NR value equals to NR equals to NR plus head difference. The head difference we need to add here directly in the numerator, because for our problem only this head difference is there. So, I equals to 1 to loop connectivity L 1. L 1 means it gives the entry in the first column. So, for the first loop we have 4 connected pipes. For 4 connected pipes, I can calculate this NR equals to KV, which is K value into QV into absolute QV to the power beta V minus 1. Again denominator, this is dr equals to dr into beta V into KV, the abs QV Li to the power beta minus 1. After taking abs, I am taking this power. So, if I divide this to numerator by denominator, this with a negative sign, I will get this QL value or del QL value. Now, this del QL value is okay, but we need to add this to our different discharge values. So, how to add this? So, let us start with the information with the loop connectivity. So, 3 rows. So, L equals to 1 to loop number. So, 1, 2, 3 for each loop can start, and I can go or I can iterate from j equals to 1 to loop connectivity L1. That means, for first loop I should use j equals to 1 to 4, for second loop j equals to 1 to 4, but third loop it is j equals to 1 to 3. So, I am checking different entries there 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3 and this is 0. Now, in this case next level is k equals to loop number. Now, we need to add this del q values. For del q I am adding this k index. If k is the index for del q and it directly matches with 1, let us say we are talking about q1 and we are in L equals to 1. So, I should add that value here, otherwise if there is no match between k and L here, I should subtract this del QL, because I need to consider or I need to update my discharge in different loops. So, after performing this operation, I will get the updated QV values. Obviously, in this case we need to calculate the RMSE value. What is this RMSE? RMSE equals to already I have used RMSE equals to 0. So, RMSE equals to RMSE plus del QL to the power 2. So, I am taking square of all discharge or increment values there. So, with this I can calculate RMSE. RMSE equals to square root of RMSE divided by loop number, because for each loop we will have one del q. So, I can display this count and RMSE value here. If there is convergence, obviously this loop, this is for while loop, this will terminated and I will get the discharge values for different loops, okay, for loops, and these are different connected pipes. Obviously, this abs value means the actual global pipe number, and QV is the discharge value with proper sign for that Lth loop. Now, if I run this, I am getting negative discharge value which is consistent with my first loop, loop 1 all negative discharge values, loop 2 I have second pipe which is having positive, 8th pipe which is having positive. So, if I see physically what is the meaning of this one. So, here in this case we have loop 1 which is initially loop 1. For loop 1, this is the loop 1. For loop 1 we are getting these negative values, this is 3184. We have assumed close values, that is why there is no change in values, almost nil, but only change is there for the last one. This is was 0.019 I am getting here as 0.0184 which is very close to this one. For loop 2 this pipe number 2 is positive, this is consistent. Pipe number 8, again this is positive, this is consistent. Pipe number 7, this is negative. Pipe number 6, this is negative. Again we are getting the same value here. Now we can change the initial distribution of discharge. If I change this initial distribution of discharge, then I should get the same value starting from specified initial discharge values. So, let us say that this is my configuration. So, what is the value here? In this case I have changed these values. This is 0.35, this is 0.2, 0.05, 0.05, 0.05, 0.1, 0.15, 0.05, but one thing is that I have not changed the direction of the flow. Whatever direction I have assumed initially, I have calculated my values based on that only. Now, if I run the same thing with configuration, because in this case the configuration part change -2, -3, -4, there is no change. 2, 8, there is no change in that one. Only change is there in terms of magnitude or values of Q. There is no change in this connectivity matrix. So, for this connectivity matrix or loop connectivity, if I open this configuration 2, which is this one, these are the specified discharge values. This is 0.35, 0.15, 0.1, 0.05, these are initial discharge values, and there is no change in the program otherwise. So, I can again iterate using this method, and interestingly I am getting convergence again, and discharge values, these are again same values are coming, minus 0.318, 0.134, 0.062, these values are same as we have got from our configuration 1. Now, let us change this configuration or direction of flow. So, let us change this direction. Now, in this case let us consider that flow is from right to left. So, flow is towards this tank which is having higher elevation. These are the values which I have got while specifying the discharge by maintaining discharge continuity at the junctions. So, these are assumed values to maintain the discharge continuity at the junction itself. So, in this case if I see the connectivity matrix, I can see that 1, 2, 3, 4. So, these 4 entries are having these 4 entries are actually positive entries. That means the flow is clockwise, and loop connectivity, if I see, this is -2 and -3. These are only 2 changes here. So, with this configuration, if I try to run my problem using Hardy-Cross method, I can see in this case we have got convergence with 21 iterations. The convergence parameter was 1 into 10 to the power minus 6 up to that level. We have set the accuracy. So, if I open this third configuration or CFG3, now only change is there for this one connectivity matrix, this 1, 2, 3, 4, these values are there. So, now if I run it, I am getting a negative value to that here. Again this is 27, 27 is the 27 is the number of iterations that is required for this one. So, what it means, this negative means this flow is counterclockwise. We have considered the flow as in clockwise direction, but it is showing that whatever value you assume by maintaining the junction continuity, you will get the exact direction of the flow. So, obviously with configuration 3 we are getting convergence here, and at the same time we can visualize the actual direction of flow from the final results. So, this was having a positive value because positive Q for these 4, but finally when I have got the results are showing negative values. That means the flow is just opposite to the assumed direction. So, with this 3 you can change different values and get the desired value for a specific network. You can also change the network configuration for or maybe you can change k values or our difference in elevation del h, or you can add pump to this problem to see what are the changes occurring during the solution process. Obviously, I have not included the pump system within these source codes. You can suitably modify these codes to add the pump consideration in pseudo loop calculations. Thank you.